These are few examples related to Coulomb's law. The first example says, consider three charges on the x-axis. Q1 is 2 microcoulomb located at x1 equals 0 meters. So this is at the origin. Q2 is located at x2 equals 4 meters. And Q3 is minus 1 microcoulomb located at x3, 6 meters. What is the value of Q2 such that the net force on Q3 is equal to 0? Let us draw the configuration we have here. So this is x equals 0. Okay, we have Q1, and Q1 is positive. So let me draw it clearly that this is positive. Now Q2, we don't know what is the value of Q2, and in fact he's asking about what is the magnitude of the charge Q2, but he gives us that the location of Q2 is at 4 meters. So this is x equals 0, and here we'll have at x equals 4, we have Q2, and it is unknown charge. So this is Q2. I put here a question mark. We don't know what is the sign or magnitude of Q2. Q3 is negative charge, and it is located at, so this is x equal 4 meters. At x equals 6 meters, so somewhere here, we have a negative charge, which is Q3. Okay, this is x equals 6 meters. Okay, and he's giving us the magnitude of Q1. It is positive 2 micro means 10 to the minus 6 coulomb, and Q3 is given to be minus 1 times 10 to the minus 6 coulomb. Micro means 10 to the minus 6, and you have to be careful about this terminology used for the charges. Would like to know what is the value of Q2 such that the net force on Q3 should be equal to 0. So F net on Q3 is equal to 0. So let us draw these forces acting on Q3. What will be the type of force between Q1 and Q3? Q1 is positive, Q3 is negative. So on Q3 there will be attraction coming from Q1. Okay, so the attraction due to Q1 will be something like this. This is the attraction along the line joining the two charges. And this force, I call it F31. This is the force on 3 due to charge number 1. Now, in order to get the net force on Q3 equals 0, the other force which is coming from Q2 should be in this direction. And it should have the same magnitude as F31. So this will be F32. This is the force coming from charge number 2 on charge number 3. The force on 3 by 2. Okay? These should be equal in magnitude, opposite in direction. Okay. In order to have this force F32 to the right, what should be the type of a charge Q2? It should be unsimilar. It should be similar. It should be negative, in order to get the repulsion. So this will be negative. This is negative, such that we will have F32 to the right. If it is positive, the force will be also to the left, and we cannot have two forces to the left cancelling each other and getting net force equals 0. So this implies that Q2 should be negative. This is very important result. Would like to know what is the magnitude of Q2. Okay, so to know it, we know that F31 should be equal to F32 in magnitude. Okay, so the magnitude should be equal in order to cancel each other. We see that their directions are opposite, and they will cancel each other if they have the same magnitude. But what is F31? It is K Q1 Q3 divided by the distance between 1 and 3 squared. Okay? And of course, I'll consider the absolute values. This is equal to K, which is the electrostatic constant, Q F32, so this will be Q2, Q3, magnitudes only, divided by the distance between them, R23 squared, the distance between charge number 2 and the charge number 3. We can see that K will cancel, so don't use it. Q3 will cancel from both sides, and we are left with Q1 divided by the distance between 1 and 3. But what is the distance between 1 and 3? We should write it here. R13, R13. What is the distance between them? It is 6 meters. Okay? What is R23? If you focus on this, my son, R23 is the distance between 2 and 3. This is x equal 4, this is x equal 6. So the distance between them will be 2 meters. Okay? So from here we can write that Q1 divided by R13, which is 6 squared, should be equal to Q2 divided by R23, which is 2 squared. Q2 we don't know, okay, but Q1 we know it. What is Q1? How much is Q1? It is 2 times 10 to the minus 6. And doing simple algebra, we will get that Q2 equals 2 times 10 to the minus 7 Coulomb. So this is the magnitude of Q2. But we know, we have decided before that Q2 should be negative. So please don't forget this minus sign. So we put here, this is negative. So I hope you understand this question. And it is very clear how to do it. We find the magnitude using the Coulomb's law, direction by simple thinking about attraction or repulsion. And of course, our point of focus is the net force on charge number 3. Thank you. This is another example on Coulomb's law, a little bit different from the previous. The previous we have all the charges on one axis, the x-axis. Here now we have two-dimensional problem. We have Q1, 2 microcoulomb is placed at the origin, while Q2 is minus Q1. So it is minus 2 microcoulomb is placed at 3 meters from the origin on the positive x-axis. A third charge Q3 has the same magnitude and sign as Q1, is placed at 4 meters from the origin on the positive y-axis. What is the magnitude and direction of the net force on the charge at the origin? So this is the application of superposition principle. We have the following. These are the charges. At the center we have Q1, and Q1 is positive. Okay. Q2 is 3 meters here, and it is negative. So this is Q2, and this is the origin. Here we have this distance, which is 3 meters. Okay, along the y-axis we have 4 meters, and there is Q3. Q3 is located there. It has the same magnitude and sign as Q1, and it is positively charged. So here we have positive. Q1 is also positive. Q2 is negative. We would like to know what is the magnitude and direction of the net force on the charge at the origin, which is Q1. Okay? Let us see. First of all, Q1 is positive, Q2 is negative, so the type of force here will be attraction. So we'll have this force, which we call F12. This is the force on 1 due to 2. Okay? It has this direction along the positive x-axis. Okay? What about the force between Q1 and Q3? This will be repulsion because positive, positive. So at the position of Q1, there will be repulsion, and it will be along the same line joining 1 and 3. And this force, we call it F13. Okay? So we have two forces are exerted on Q1 due to Q2 and Q3. Okay? This question is asking what is the magnitude and direction of the net force on the charge at the origin. Okay, let us calculate F12. Of course, the net force will be something here. Okay? This is F net. Would like to know how much, what is the magnitude of this F net and what is its angle theta it makes with the positive x-axis. Okay? This is the x-axis and that is the positive y-axis. So F12 equals K Q1 Q2. Of course, I talk about magnitudes only, absolute values, divided by the distance between 1 and 2, which is 3 squared. Okay? How much is that? Let us plug in the numbers. I'll have 9 times 10 to the power 9 Q1, which is 2 microcoulomb, so 2 times 10 to the minus 6 coulomb, multiplied by Q2. It has the same magnitude, so it is 2 times 10 to the minus 6, okay, coulomb, again, divided by 3 squared. And from here, we will get F12 to be 4 times 10 to the minus 3 Newton. This is the magnitude of the force. But what is the direction of this force? It is in the positive x-axis, so I'll write I here. Okay, so this is the direction, and this is the force as a vector. It has this magnitude, and it is directed in the positive x-axis. Nice. Let us do the same for F13. F13 will be K, Q1, Q3, magnitudes, of course, divided by the distance between them, which is 4 meters. So this will be 4 meters squared. Don't forget the square, my son. Okay? This will be 9 times 10 to the power 9. I'll have 2, 10 to the minus 6, multiplied by 2, 10 to the minus 6, okay, divided by 4 squared, which is 16. If you do this calculation, you will get F13 to be 2.25 times 10 to the minus 3 Newton. This is the magnitude of the force. But what is the direction? I can see the direction. It is along the negative y-axis. So this is minus j in the negative y direction. And here I'll put the arrow indicating that this is the force vector. It has a magnitude and it has a direction. Now, if we'd like to know what is F net, F net equals F12 plus F13. But how much, what is the magnitude of this F net? F net, using Pythagoras theorem, this will be square root of F13 squared plus F12 squared. Okay, so I'll take these two and square them. Simple calculation, we will get the net force, which is approximately 4.6 times 10 to the minus 3 Newton. Okay? Would like to know what is this angle theta? What is this angle theta? This angle theta has the adjacent, which is F12, it has the opposite, which is F13. So this is F13. This is the same as that. And the neighbor, which is F12. So tan theta, or theta will be tan inverse of the y component divided by the x component. So this will be tan inverse of F13 divided by F12, which is the x component of the net force. And this will be very simple. We will get tan inverse of these two numbers. We will get theta 29.4 degrees, and we can see that it is along in the fourth quadrant. Okay, this is from positive x axis clockwise, or in fourth quadrant. So it is very simple vector algebra, where we had similar questions in Physics 101. So please, my son, you have to make sure that you understand the vector algebra, how to add vectors, how to find the magnitude of a vector, how to find the direction and the angle of a certain vector. Thank you. This is the last example related to Coulomb's law. We have two small identical conducting spheres initially uncharged. So they are neutral. Number of electrons equals number of protons in these two small spheres. They were separated by a distance of 1 meter. This is the separation between the two small spheres. Would like to know the number of electrons that must be removed from one sphere to the other sphere in order to produce an attractive force of this much between the spheres. Okay? So this is the situation. We have a small sphere. Of course, here it's very important to have this word, small sphere. Otherwise, he should tell us what is the radius of each sphere. Okay? Because the separation between them is 1 meter. Okay? Due to shell theorem, they will attract each other as if all the charge is focused at the center. Okay? So if it is very small, half centimeter radius, and here half centimeter radius, it is negligible when compared to the 1 meter separation between them. Okay? But if it is large, if it is say for example 30 centimeter, the radius here and the radius there, the separation, we should add to this 1 meter the radius of the first sphere and the radius of the second sphere. But he didn't tell us anything about the size of the sphere, except telling that it is very small, meaning that it is negligible. The radius of each sphere is negligible. Okay? So first of all, there is no force, there is no electrostatic force between the two spheres, because they are neutral, they are uncharged. So there is no electrostatic force. If we remove a certain charge from the first, okay, so we remove electrons from here and transfer it, add electrons here. The same number of electrons which we remove from the first, we will put on the second. So if we remove from here, this will be positively charged. Okay, so this will be plus Q. Okay, and we'll put it there. So here we'll have excess of electrons. So here we'll have the same magnitude but with opposite sign, minus Q. Here we'll have plus Q, and there will be minus Q. And due to quantization of a charge, Q here is nothing but N multiplied by the charge of electron. And here this will be minus N, the charge of the electron. This is negative, and this is the same amount, but it is positive. Okay? And he's telling us that the force of attraction, of course it will be attraction because we have negative, positive, unsimilar charges, there will be attraction between them. And the force of attraction has this magnitude, which is 2 times 10 to the power 4. So we can apply Coulomb's law. We have the force of attraction between them has a magnitude of K, Q1 and Q2. So it is Q squared divided by the distance between them squared. Okay? And it is given, this magnitude is given to be 2 times 10 to the power 4 Newton. It is a very large force, equals K, which is 9 times 10 to the power 9. This is electrostatic constant. Q squared, but each Q, we are interested with this magnitude. Huh? Don't worry about the sign. So this will be N multiplied by E, N squared, E squared, divided by R squared, which is 1 meter squared. So from here, we know E, this is squared. Huh? This is the charge of the electron squared. This is N, which is the number of electrons, the integer multiple of electrons. And he's asking us, find the number of these electrons. Okay? And from here, we can get that N squared equals 2 times 10 to the power 4 divided by the charge of the electron squared. So this will be 1.6, 10 to the minus 19, all squared. But if you would like to find the number, so we need to have the square root of all of this, and this will give us the number of electrons, and it is a huge number, which is 9.3 times 10 to the power 15 electrons. Okay, so this is the number of electrons which will be removed from one sphere to the other to give us this attraction force between them. Thank you.